Your everyday world looks solid, stable, logical, but if you could zoom in, way down, past what any microscope can see, you'd find that reality starts to behave in ways that break all our common sense rules. It gets weird. In this video, we're going to decode quantum reality, and along the way, we'll uncover the crucial details that most popular explanations leave out. So what does quantum even mean? Forget the complicated jargon for a moment. Quantum simply refers to the world of the very, very small, the realm of electrons, photons, and individual atoms. Down here, the rules that govern our world, the world of footballs, cars, and coffee mugs, no longer apply. The universe plays by a different set of rules, and that's precisely where all the confusion begins. But stick with me, because it's not as scary as it sounds. Let's start with a big one: superposition. You've probably heard the mind-bending phrase that a quantum particle can be in two places at once. This isn't some kind of magic duplication trick where a particle clones itself. It's more subtle and, frankly, more profound. It means that before we interact with it, before we measure it, the particle isn't in a single, fixed state. Instead, it exists as a spread of possibilities. It's not in place A or place B. It's in a state that includes both A and B. And here's the part most people miss. Superposition doesn't mean a tiny ball is literally sitting in two different chairs at the same time. That's a misleading image. A better way to think of it is as a probability cloud, or a wave of chances. This wave describes all the potential places the particle could be, and how likely it is to be in each one. Reality at this level is fuzzy. It's only when we perform a measurement that this cloud of possibilities collapses into one single, definite result. Before that moment of interaction, the particle is pure potential. This leads us to another core idea: wave-particle duality. Experiments have shown, without a doubt, that tiny things like electrons and photons can behave as both waves and particles. How? Well, if you shoot electrons one by one towards a screen, they make interference patterns just like waves in water would. But at the same time, each electron lands on the screen at a single, precise point, like a tiny billiard ball. So which is it? The quantum answer is, it's not either-or. It's both, and which behavior you see depends entirely on how you set up your experiment to look at it. Now for what you might have missed. These quantum objects don't have a little consciousness deciding, okay, for this experiment, I'll be a wave, and now I'll act like a particle. It's our measurement setup that coaxes out one aspect or the other. When we design an experiment to measure its wave-like properties, we see a wave. When we design it to find its location, we see a particle. The mystery is real, but it's a mystery of fundamental physics, not a cartoon superpower where things change shape on a whim. This is perfectly illustrated by the famous double-slit experiment. Imagine a barrier with two thin, parallel slits in it. If you fire particles, say electrons, at this barrier, what do you expect to see on the detector screen behind it? Just two bands right behind the slits? Wrong. With both slits open, you get a complex pattern of many bands, an interference pattern. This is classic wave behavior. But here's the twist. If you place detectors at the slits to find out which one each electron goes through, the interference pattern completely vanishes. Now you just get two simple bands. The very act of measuring the path changes the outcome. This is where many people get led astray. The word observation makes it sound like a conscious human being has to be watching. That's not it at all. Observation, in quantum mechanics, simply means any interaction with a measuring device or the wider environment. A particle bumping into a detector, a photon bouncing off an atom, any process that records information about the particle's path is enough. Once information about which slit the particle went through is out there in the world, the quantum fuzziness sharpens into a classical result. No human attention required. Next up is Werner Heisenberg's famous uncertainty principle. It states a fundamental limit to our knowledge. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. It's a trade-off. You can pinpoint its location, but then its speed and direction become a blur. Or you can lock down its momentum, but then its location spreads out into a wave of possibility. This isn't because our instruments are clumsy or our hands are shaky. It's a built-in feature of nature itself. And here's the crucial detail. This isn't a problem with our tools. It's not that our microscopes are too weak or that we're disturbing the particle by looking at it. The principle points to something deeper. At the quantum scale, properties like position and momentum aren't just independent numbers you can write down. They are linked in a fundamental way. Reality itself comes with a certain amount of uncertainty baked right in. You can't know everything about a particle at once, because everything doesn't exist to be known in that way. Then there's entanglement, an idea so strange that Albert Einstein famously called it spooky action at a distance. You can create two particles that are intrinsically linked or entangled. Their properties, like spin, become perfectly correlated. If you measure one particle and find its spin is up, you instantly know the other particle's spin is down, no matter how far apart they are, even if they're on opposite sides of the galaxy. It seems like they are communicating instantly. But here is the part that most popular science stories skip. Entanglement does not allow you to send messages faster than the speed of light. While the connection is instant, you can't use it to send a signal. Why? Because the outcome of your measurement on the first particle is completely random. You do not know if you will get it up or down until you measure it. You only discover the perfect correlation later, when you and your friend on the other side of the galaxy compare notes using normal, slower-than-light communication, like a phone call. Physics is spooky, but it doesn't cheat Einstein's laws. So if all this quantum weirdness is real, why don't we see it in our daily lives? Why isn't your chair in a superposition of being in the living room and the kitchen? The answer is a process called decoherence. Large objects like chairs, cats, and people are constantly interacting with their environment. They're being bombarded by air molecules, photons of light, and thermal vibrations. Each one of these tiny interactions acts like a measurement, collapsing the delicate quantum state. A big object loses its quantum fuzziness almost instantly. Decoherence isn't some magic wand that solves every mystery, but it beautifully explains why the everyday world looks so solid and predictable. The environment itself is constantly measuring everything in it, forcing complex systems into stable, classical states long before our eyes ever get involved. The quantum weirdness is still there, but it gets washed out on a massive scale. One quantum effect that does sneak into our world is tunneling. Imagine throwing a ball at a wall. It will always bounce back. But a quantum particle, because it's described by a probability wave, has a tiny, non-zero chance of simply appearing on the other side of a barrier it shouldn't be able to cross. It doesn't punch a hole. Its probability wave leaks through the barrier. This isn't just a weird theory, it's a fundamental process that makes modern technology possible. In fact, quantum physics isn't just an abstract idea. It's deeply embedded in the technology you use every single day. The transistors in the computer chips that power this video rely on quantum tunneling. Lasers work because of how electrons jump between quantum energy levels. MRI scanners in hospitals use the quantum property of atomic nuclei. Solar cells, LEDs, and even the atomic clocks that make your GPS accurate, all of these technologies depend on quantum mechanics working exactly as the strange equations predict. Unfortunately, the weirdness of quantum physics has been hijacked to sell all sorts of pseudoscience. You'll see videos claiming quantum mechanics proves that your thoughts create reality, that you can manifest a new car through observation, or other mystical shortcuts. But quantum theory is a rigorous mathematical branch of science. It's already strange, beautiful, and mind-bending on its own. It doesn't need these fake spiritual upgrades. So, what is the real mystery that remains? Here's the honest truth. The equations of quantum mechanics work perfectly. They make the most accurate predictions in the history of science. But what those equations truly mean about the nature of reality is still hotly debated by physicists and philosophers. Interpretations like the Copenhagen model, the many worlds theory, or pilot wave theory all use the same math and make the same predictions, but they tell very different stories about what's happening behind the scenes. The physics is complete, but the philosophy is wide open. When you pull back and look at the big picture, you see that quantum reality isn't random chaos. It's an incredibly precise, structured, and testable framework. It reveals a universe that is less like a collection of solid, separate bricks, and more like an interconnected web of patterns, probabilities, and interactions. Once you begin to grasp that, our normal reality starts to feel a little too simple, and you realize the universe is far deeper and more mysterious than we ever imagined. Thanks so much for exploring this with me. If you enjoyed this journey into the quantum world, don't forget to like, subscribe, and hit that notification bell for more deep dives into science. See you in the next one.